In this video, we're going to talk about the equation for spring force. So we're going to write that out here. It is F sub S equals K times X, where F sub S is our spring force, K is our spring force constant, and X is the amount of displacement that the spring sees. So maybe you're compressing a spring, or maybe you're stretching a spring, but X is the amount of displacement that the spring sees. So let's say that we've got, some kind of wall, got a hard stop here, and we've got a compression spring right there, and we want to apply a force to that compression spring and reduce it to half its original length. So let's say that its original length here is, 10 inches. That's kind of a long extension spring. Why don't we say its original length is 3 inches. And we want to compress it to 1.5 inches. So first off, what is X for this this problem here? And remember, X is the amount of displacement for that spring. So we're taking it from 3 inches to 1.5 inches. So how far are we compressing that spring? It's going to be just 3 inches minus 1.5 inches equals 1.5 inches. We're compressing it by 1.5 inches. Now your spring constant, is going to be given to you by the supplier. So you might look up on McMaster-Carr or whoever the spring supplier is, and you'll find the spring constant. And your spring constant is always going to be given to you in terms of pounds per inch. Well, I should correct that. It's always going to be given to you in terms of force per distance. If we're saying right now that we're using English systems, then then it would be pounds per inch. Sorry, I had some notifications there in the background. So going back to our original question, how much force is required to compress this spring to half its original length? Well, we get our equation here, F sub S equals, and let's say that we looked up this particular spring that we're using, and the spring constant is, maybe 2 pounds per inch, something like that. And so our equation F sub S equals K times X. So our spring constant is 2 pounds per inch, and we are compressing it by 1.5 inches, 1.5 inch. Inches cancel out. We're left with just pounds, and that equals 2 times 1.5, which is going to be 3 pounds force. So 3 pounds of force are required to compress the spring to half its distance. So let's see, how else could we do this? We could say instead of how much force is required to compress it to half its length, why don't we say if we compress this 3/4, or let's just say if we compress this spring down to 3/4 of an inch, how much force would the spring be pushing back with at that point? Hold on, is that what we want to do? Let's do it a little bit differently. Let's say what if we apply 4 pounds? Let's say let's make it something not so clean. 4.3 pounds of force. If we apply 4.3 pounds of force right here, to what compressed length are we going to compress that spring? Right? So we can start with the same equation, right? F sub S equals K times X. Only this time we're solving for X, not for our spring force. So we'll reconfigure this equation. We'll say X equals F sub S divided by K. Then we'll say equals, so we know that F sub S we're saying is 4.3 4.3 pounds of force divided by K, which is 2 pounds per inch. So in this case, the pounds force ends up canceling out, and we're left with equals 4.3 over 2 inches. And so let's see, 4.3 divided by 2 is 4.3 divided by 2, 2.15 equals 2.15 inches. Okay, so now remember that what we have solved for is not the new length of the spring yet. What we've just solved for is x, so the amount of deflection, or in other words, how far we've pushed the spring. So remember, the spring started out at 3 inches long, right? And we have found that if we place 4.3 pounds of force on that spring, it will deflect by 2.15 inches. So to get the new length of the spring, what we have to do is say 3 inches minus 2.15 inches, which equals 0.85, I think, 0.85 inches. And that would be the new length of the spring. Now, of course, this only works up to a certain point, because at some point you're going to end up with a spring that, you know, is fully compressed, and you can't compress it anymore because it's just solid material there now. There's no longer a distance between each spring loop. It's just solid, fully compressed. So your supplier will also tell you what that fully compressed length is, and oftentimes there's a recommended compressed length that is a little bit thicker than the theoretical fully compressed length, and that's just to preserve the life of that spring. So sometimes if you fully compress a spring, it can actually plastically deform, or if it doesn't plastically deform, maybe it just reduces the life of the spring, so that instead of holding up for 1,000,000 cycles, maybe it holds up for only 20,000 cycles or something like that before it might start plastically deforming or losing its nominal spring characteristics. So anyway, that is how to use the spring force formula.
If you found this content helpful, consider enrolling in our signature program at mypipelineacademy.com. Whether you're an individual interested in beginning a new career as a mechanical designer, or a company interested in training your new engineering hires, our signature program helps students develop the practical skills they need to be productive mechanical design engineers. Seating is limited. We hope to see you there soon.